Welcome to AI Frontiers, where we explore the cutting-edge research reshaping artificial intelligence. Today, we're diving into machine learning's latest breakthroughs, examining 82 research papers from November 3, 2025, all from the computer science machine learning domain. These papers span an incredible range of applications, from quantum computing to medical diagnostics, representing the research that's actively reshaping our understanding of artificial intelligence. What will we discover on today's journey through modern machine learning research? First, we'll explore the current landscape and provide a comprehensive field overview. Then we'll examine 4 dominant research themes that are emerging from this collection of work. We'll highlight groundbreaking findings across diverse applications, analyze the methodological innovations driving progress forward, and finally discuss the future directions that are shaping tomorrow's artificial intelligence capabilities. Computer science machine learning serves as the mathematical brain of artificial intelligence. This field develops algorithms and statistical models that enable computer systems to learn from experience rather than being explicitly programmed for every possible scenario. It powers the recommendation systems suggesting your next favorite movie, the medical diagnostic tools detecting diseases earlier than human specialists, and the autonomous vehicles navigating complex traffic patterns. This interdisciplinary field draws from statistics for mathematical foundations, computer science for computational frameworks, and cognitive science for understanding learning processes. It has become the invisible backbone of our daily digital lives, with growing impact across virtually every sector of human activity. The first dominant theme centers on robustness and reliability in machine learning systems. This encompasses research into making models more resilient to various forms of noise, adversarial attacks, and distributional shifts. Researchers are exploring how different loss functions affect the robustness of matrix sensing problems, particularly when dealing with non-Gaussian or heavy-tailed noise. Their work on kernel optimal loss functions demonstrates how traditional mean-squared error approaches can fail under challenging conditions, while robust alternatives maintain stability. Similarly, quantum-enhanced generative models specifically target rare event prediction, addressing the notorious difficulty that classical models have in capturing low-probability but high-impact events. This theme reflects the growing deployment of machine learning systems in high-stakes environments where failures can have serious consequences. The second prominent theme focuses on efficiency and optimization in machine learning systems. This includes both computational efficiency and theoretical foundations. We see increasingly sophisticated analyses that provide tighter bounds and better understanding of algorithm behavior. Variance-aware Thompson sampling for contextual bandits exemplifies this trend, providing optimal regret bounds for previously understudied algorithm classes. The flashlight framework represents another angle, offering a compiler-native approach to generating fused attention kernels that enable efficient execution of diverse attention patterns without requiring hand-tuned implementations. This emphasis on efficiency reflects the growing maturity of machine learning as it moves from research laboratories to real-world applications. Mobile devices have limited battery life and processing power, edge computing systems need to make decisions quickly with minimal resources, and large-scale systems must handle millions of users simultaneously. The third significant theme revolves around interpretability and understanding of learned representations. As machine learning models become more powerful and are deployed in critical applications, understanding how they make decisions has become paramount. Researchers are working on improving our understanding of various learning mechanisms through novel analytical approaches. Contrast-consistent search uses contrastive eigenproblems to better understand learning dynamics, while other research investigates the intrinsic dimensionality of geographic representations learned by neural networks. Perhaps most intriguingly, attention-based models are being used as automated data auditors, uncovering hidden biases that might otherwise go unnoticed. In clinical gait analysis, researchers discovered that attention mechanisms revealed severe dataset biases where models assigned over 70% attention to the right foot while statistically ignoring the left foot, exposing a critical laterality bias in public datasets. The fourth theme encompasses federated and distributed learning paradigms, reflecting the growing importance of privacy-preserving and decentralized learning approaches. Researchers are addressing challenges like submodular maximization in federated settings while maintaining robustness against malicious clients. This work is crucial as machine learning systems increasingly need to learn from distributed data sources while preserving privacy and security. We also see a strong emphasis on domain-specific applications that demonstrate machine learning's expanding reach into specialized scientific fields. This includes fusion science applications for predicting coil deflections in fusion reactors, microbial ecology work using graph neural networks to predict interspecies interactions, and various other applications that showcase how machine learning is becoming an essential tool across diverse scientific disciplines. Among the wealth of research presented, 5 findings stand out as particularly groundbreaking. First, variance-aware Thompson sampling work achieves optimal regret bounds for contextual bandits with general reward functions, not just linear ones. This represents a significant theoretical advance because most previous work focused on upper confidence bound-based algorithms. Second, research on clinical gait analysis revealed that attention-based models can serve as automated data auditors, uncovering hidden biases that might otherwise go unnoticed. Third, researchers discovered that adding explanations to labels during fine-tuning improves model performance, but surprisingly, even syntactically incoherent pseudo-explanations provide substantial benefits. Fourth, quantum-enhanced generative models demonstrate up to 50% reduction in tail divergence compared to state-of-the-art classical methods. Finally, research on intrinsic dimensionality provides the first systematic study showing that despite having ambient dimensions between 256 and 512, the intrinsic dimensions of geographic representations fall between 2 and 10. The papers reveal several methodological approaches that have become fundamental to modern machine learning research. Thompson sampling and Bayesian approaches maintain probability distributions over model parameters and make decisions by sampling from these distributions, naturally incorporating uncertainty while achieving optimal theoretical guarantees. Attention mechanisms and transformer architectures excel at capturing long-range dependencies and providing interpretable weightings of input components, as demonstrated in both efficiency frameworks and clinical applications. Online learning and adaptive algorithms excel at handling non-stationary data streams and adapting to changing environments without requiring complete retraining. Graph neural networks and structured representations leverage relational information to improve predictions, achieving impressive results like F1 scores over 80% in microbial interaction prediction. Finally, hybrid classical quantum approaches represent an emerging methodology that potentially offers advantages in sample diversity and exploration of complex probability landscapes. Let me examine the first selected paper on variance-aware Thompson sampling for contextual bandits by Lee and colleagues. This work addresses a fundamental problem in online learning where we must make sequential decisions based on contextual information while balancing exploration and exploitation. The contextual bandit problem is central to many real-world applications, from personalized recommendations to clinical trial design. The researchers' primary objective was developing a Thompson sampling algorithm that achieves variance-dependent regret bounds for contextual bandits with general reward functions. Previous work largely focused on upper confidence bound-based algorithms, leaving Thompson sampling understudied despite practical advantages in computational efficiency and empirical performance. Their key technical innovation lies in handling variance-dependent terms in regret analysis, developing new concentration inequalities that bound regret in terms of cumulative variance rather than just the number of rounds. This research bridges an important gap between theory and practice in online learning. The second selected paper examines matrix sensing with kernel optimal loss by Song and colleagues, addressing how loss function choice affects both robustness and optimization landscape of non-convex problems. Matrix sensing, where we recover a low-rank matrix from linear measurements, is canonical in high-dimensional statistics with applications from collaborative filtering to phase retrieval. The researchers aimed to understand how robust loss functions derived from nonparametric regression principles can improve both solution stability and optimization geometry compared to traditional mean-squared error approaches, particularly with non-Gaussian or heavy-tailed noise. Their methodological approach elegantly proposes a kernel-based estimate of residual density, maximizing estimated log likelihood instead of using mean-squared error loss. This robust formulation coincides with traditional loss under Gaussian errors but remains stable under general noise conditions, naturally adapting to underlying noise distribution without requiring prior knowledge. Experimental validation demonstrates clear advantages across various noise distributions, with the robust approach maintaining stable performance while traditional methods degrade significantly. The third selected paper investigates measuring the intrinsic dimension of Earth representations by Rao and colleagues, tackling fundamental questions about information content in geographic machine learning models. As Earth observation data becomes increasingly available and geographic implicit neural representations become widely used, understanding what information these models capture and how efficiently they encode it becomes crucial for scientific understanding and practical applications. Their research objective was providing the first systematic study of intrinsic dimensionality in geographic representations, which embed low-dimensional location inputs into high-dimensional embeddings through training on satellite imagery, text, or other geo-referenced data. Key findings reveal that despite high ambient dimensionality, intrinsic dimensions typically fall between 2 and 10, suggesting these models capture relatively low-dimensional structure in Earth data. The research demonstrates that intrinsic dimension correlates with downstream task performance, providing a label-free metric for model evaluation. Most importantly, intrinsic dimension can capture spatial artifacts and facilitate model diagnostics. This work provides the first architecture-agnostic, label-free metric for evaluating geographic representations. Looking toward future directions, the field faces several important challenges and opportunities. Theoretical sophistication continues advancing with increasingly complex analyses providing tighter bounds and better algorithm understanding. However, this creates a growing gap between theoretical capabilities and practical needs, with many rigorous results making assumptions that may not hold in real-world applications. The emphasis on robustness and reliability represents another crucial trajectory, with multiple approaches addressing various aspects of making machine learning systems more dependable. Efficiency considerations are driving innovations in both algorithmic design and hardware-software co-design, with specialized frameworks for attention mechanisms and exploration of neuromorphic computing approaches. The integration of machine learning with domain-specific knowledge represents another important direction, with researchers increasingly recognizing the value of incorporating domain expertise, physical constraints, and scientific principles into learning algorithms. Finally, the development of new mathematical frameworks and computational paradigms, including quantum-enhanced approaches, suggests that the field may be on the verge of fundamental advances. This analysis was synthesized using Claude Sonnet 4i model, with text-to-speech synthesis powered by Google technology and image generation capabilities provided by Grok. The content has been reviewed by a human machine learning expert to ensure accuracy and clarity. While every effort has been made to accurately represent the research findings and their significance, potential oversights are acknowledged. All original research papers are available through the archive preprint server, and we encourage listeners to explore the primary sources for complete technical details. The interdisciplinary nature of machine learning research means that some nuances may require domain-specific expertise to fully appreciate. This synthesis aims to make cutting-edge research accessible while maintaining scientific rigor, but listeners are encouraged to consult the original papers and additional sources for comprehensive understanding. Subscribe to our YouTube channel for weekly updates and join thousands exploring AI's future together. We provide deep dives into cutting-edge AI research with expert analysis of breakthrough papers. Hit the bell icon for notifications so you never miss an episode. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archived preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archived preprint server.